Now we have the ingredients, we understand enough about the solar nebula to start following the process of how we got from a disk of gas and perhaps some dust to what we have today. And we'll start with the interior planets, the terrestrial planets. Remember that inside the snow line, we have mostly hydrogen and helium gas, but in addition, there are small amounts of solids that congeal. The solids in question are iron and nickel, silicates, the kind of materials we find in meteorites, and there's not a large quantity of those because these elements are very rare in the nebula, but there's enough. And as the density increases, these dust grains that are in Keplerian orbits inside this massive cloud of dust collide with each other and they adhere. They adhere in the same way that grains of dust adhere to cleaning rag. They adhere electrostatically and then chemically bind. They're forming rocks. These rocks are held together by chemical forces. And slowly over time, the larger rocks have larger surface area. They collide with more of the dust. And they grow, and eventually one forms objects of a size order of magnitude of a kilometer. There will be about 1 billion of them in the inner solar system. And these billion so-called planetesimals, microplanets, are reaching a size where, as we'll see in the homework, when you reach a size of about 1 kilometer, an object is bound now by its gravitation. In other words, the gravitational force is enough to hold the object together. It's more gravitationally bound than chemically. And this is an important transition because now these objects are heavy enough that they're moving in Keplerian orbits. They are no longer sustained by the pressure of gas, which is still enough to hold up. The dust is floating in the gas, but the larger rocks are not floating in the gas. They're falling through it, so they're moving on Keplerian orbits. Their velocities are higher than those of the gas and the dust, and so these large planetesimals are sweeping through the gas, and whatever grains of dust come close are immediately falling onto the planetesimals and being gravitationally attached. And so the gravitational attraction becomes important, and the larger objects grow faster. So there is this hierarchical growth where the rate at which an object grows turns out to be proportional to its radius to the fourth. And this goes on for about 100,000 years, in which these planetesimals, and certainly the larger among them, grow up to be rather large objects. And through these, at the end of this 100,000 years, the largest of them have merged to form about a few hundreds of objects that are called protoplanets. These are objects with a radius on the order of 1,000 kilometers, so slightly smaller than the current moon. And here another important transition happens. When you reach a radius or a size of about 1,000 kilometers, the object is certainly gravitationally bound. What has been holding up the rocks so far, the reason a rock doesn't collapse under its own gravity, is basically that a rock is rigid material. Chemical bonds hold it up against its own gravity. When an object reaches 1,000 kilometers, two important things happen. One is the heat of the collisions and the Kelvin-Helmholtz heating from converting gravitational potential energy as objects collide into heat, along with the radioactivity. The heat released by the radioactive elements that are trapped inside melts a protoplanet. When you reach a size of about 1,000 kilometers, you melt. This is very important. Things that melt are going to be spherical. Why are they going to be spherical? Well, because gravity flattens them out to the form of a sphere. Imagine a molten liquid Earth. We have parts of the Earth that are liquid. They are the oceans. There are no mountains in the ocean because a mountain in the ocean would be leveled by gravity. When the Earth was molten, and where a protoplanet is melted and liquid, it will naturally form into a symmetric spherical shape. If it is twisting, if it is spinning, it will be slightly oblate, slightly fatter at the equator than at the poles because of, again, the centrifugal barrier that we talked about. But as long as it's not spinning too rapidly, it will be approximately spherical. This is one important process that takes place. All of these protoplanets are assuming spherical shape. And then the other important thing that happens at 1,000 kilometers when things melt is something called chemical differentiation. These initially roughly uniform objects where various elements were scattered haphazardly depending on when they were accreted throughout the object become segregated, because once an object melts, then the heavier elements, iron, nickel, sink through the lighter silicates, say, down towards the center, and one forms a chemically differentiated object where there forms a core which is rich in the heavier elements, iron, nickel, etc., along with an external envelope, which is the silicates, and much cooler crust as the core, as infalling matter falls in, we get additional heat at the crust. In addition, once an object is fluid, it's no longer held up by the chemical bonds, by rigidity. What holds the Earth, or a protoplanet, up against collapse under its own gravity is hydrostatic pressure, the same kind of hydrostatic pressure balance that held our slinky in balance, or the water in our cup. Pressure is largest in the middle, decreases as you move up through the Earth. Each layer is in hydrostatic equilibrium, its weight balanced by the extra pressure below it compared to the pressure above it. And so we obtain high pressure and high temperature in a core with decreasing pressure and temperature towards the outside. This is the situation in a planet. This happens when you create a protoplanet. So the transition from planetesimal, an object which is bound by gravity, but where gravity is not yet dominant, to a protoplanet which melts, becomes spherical, and chemically differentiates, is the transition that we go through. After about 100,000 years, we have generated protoplanets, a few hundreds of protoplanets, orbiting the sun in this region that will become the inner solar system within about 2 or 3 astronomical units from the sun. How do we know about protoplanets? Well, we're fortunate enough to have some of them left. What we see in this beautiful video clip is an image of an actual protoplanet. This is the asteroid Vesta, as imaged, as it says, by the Dawn spacecraft in 2011. The spacecraft was orbiting the asteroid, and so it got to take a 360-degree panoramic image. We see the roughly spherical shape. We see the impact craters. We have to talk about what created those. This is an object that melted as it contracted gravitationally, so it's roughly spherical. The asteroid Vesta is an interesting object in itself. It will be visible this winter. It will be in opposition, and if you get a chance to go out and take a look with a sufficiently large telescope, you're invited to view Vesta. You won't get a view like this, though. Carrying on with our plan of producing planets, we now have these protoplanets orbiting. They rapidly gravitationally accrete the remaining planetesimals. So now what goes on is that the gravitational force of these protoplanets begins to be important, and their interactions with the planetesimals are gravitational. They either accrete the planetesimals, or if they collide with them, they might blow them up and eject them from the inner solar system. The result of this process is that you end up with about 100 objects the size of the Moon, Mars, so smaller than the Earth. These are the protoplanets, and they have cleared gaps in the disk. So where a protoplanet is orbiting, there will be no more planetesimals. Planetesimals will still be orbiting. In the gaps between, these will be about 100 equally spaced orbits between the interior of the disk, just outside the sun, and say 2 or 3 astronomical units out. And in this region will be 100 protoplanets orbiting in cleared gaps, and in between them there will still be planetesimals. Now, the gravitational interactions between protoplanets themselves now become important. We'll talk about that in the next clip. And this distorts their orbits so that they start moving through these gaps, ejecting or accreting the remaining planetesimals. These distorted orbits now lead to actual collisions between the protoplanets. And these collisions are massive collisions. These are moon-sized objects crashing into each other with Keplerian velocities. This can lead to a complete destruction of some of the objects. The collisions are now violent. And there's some suitable conditions. The two objects partially remelt and merge, and this leads from these 100 or so moon-sized objects to a few large ones like Venus and Earth. this is where the larger planets come from these mergers of these protoplanets. One such collision, we think, left Mercury stripped down to its core. We'll see that Mercury is a very dense planet. The explanation is that a collision evaporated and blew off into space its envelope, leaving just essentially the core. Mars never grows beyond a Mars-sized object. It's smaller, it's about the size of the moon, it's much lighter than Earth. We'll see what it is that limits or stunts the growth of Mars. And within 10 to 100 million years, remember 10 million years is when the dust is gone and the gas is gone, the T-Tauri winds clean out the system, and the orbits which have been perturbed settle down by mutual friction down into the near circular orbits that we see. So within 10 to 100 million years, we have pretty much the inner solar system as we know it. We see this in this beautiful video. We start with the orbiting clouds of planetesimals. We see the gaps where larger protoplanets are forming. In a minute, we'll be able to see the actual protoplanets. Here's a protoplanet. And the planets, as they orbit, clear away lanes inside the planetesimals, and slowly their influence cleans out the leftover planetesimals, either accreting or ejecting them, so that after about 10 million years, we are left with roughly the solar system as we know it, and the sun blows away the remaining gas and dust, and we find the interior solar system, or the inner solar system, looking pretty much the way we see it today. What happens beyond is going to be the subject of the next clip.